Warning: the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video for trig and college algebra students, we're going to start our investigation or re-investigation of exponential and logarithmic functions. To be very honest with you, it is assumed that you've been pre-exposed to exponential functions, as it is a prerequisite for college algebra to have already gone through all of exponential and logarithmic functions. So what's going to happen here is it's just going to be a high-level review. Not the same high-level review that I would give to a pre-calculus class, but close to that level, to be very honest with you. So let's start right into it. This video will just be dedicated to kind of the overview of what an exponential function is, to remind you of the small little things you might have forgotten. First thing we need to talk about is, what is an exponential function? Well, an exponential function is a function of the form p of t is equal to p naught b to the t power. Your textbook likely doesn't write it this way. Most textbooks will write it this way. F of x is equal to a times b to the x. They're the same statements, just one textbooks call it f, and I call it p. Because generally speaking, when you're talking about exponential functions, you're talking about population models. So a population that's growing, a population that's decaying, whether it's bacteria or human populations or animal populations, whatever it may be. It's a population of something, money even. So that's why I prefer to use p of t, and t specifically because, well, exponential functions are generally speaking functions of time. And so I just like to use this notation. P sub 0 is the population at time 0. So I'm not going to write out the whole word population. So I'll just say population at t equals 0. So that is called an exponential function. The base of the function is b. And by definition, b must be positive, and it can't be 1. Why can't it be 1? Well, imagine that somebody says you have some population that's growing exponentially, and they tell you, yeah, and the base is 1. Well, if it's 1, then 1 to any power is still just 1. And so this would be p naught times 1, or p naught. In other words, this population would never change if the base were 1. So that's why we do not allow the base to be 1, because the population would never grow, nor would it decay. Then there's another restriction, that the population, or not population, but the base must be positive. That's this piece right here. But why is it that we require the base to be positive? It's very simple, actually. If you allow the base to be negative, so pretend for a moment that we were to be okay with that. So let's say I put in here a negative, I don't care, 2. Okay. Then you have a problem with certain values of time. For example, a half a day later, what is the population? P of 1/2. What is the population when time is 1/2? Well, remember what the exponent of 1/2 means. It means the square root. And so we have the square root of -2, and that's a problem. We do not want imaginary solutions or imaginary values to our function. And because of that, we restrict the base of our function to be positive. What else can we talk about here? I already said that p naught, that's the initial value. So that's the population at time 0, or the time 0 population. That's the basic structure of an exponential model, or an exponential function. So continuing forward with our review of exponential functions, there's a little theorem here. The exponential function p of t, which is p naught b to the t, where p naught, in this case, we're forcing p naught to be positive. Now, this is something that normally you would not see in a textbook. But the reason why I'm saying we're going to just force p naught to be positive is because, generally speaking, with exponential models, your initial population is not going to be negative. Exponential functions are generally used to model real-world situations. There's no such thing as a negative population. Actually, I shouldn't say there's no such thing. I should just say it's incredibly rare, if at all. So, we are going to assume that our initial population is positive. Then if that's the case, that exponential function is increasing if the base is greater than 1, and decreasing if the base of the exponential is between 0 and 1. And before I get to the second sentence, which is dealing with when the population, the initial population, is negative, so this piece right here, before I get there, let's just draw out why we have an increasing population when the base is greater than 1. So let's suppose this was actually a problem that was presented in the Lucille show, which is the Lucille Ball show of I Love Lucy. She went to her boss, and I forget the name of the episode, honestly, it doesn't really matter, but she went to her boss and asked for a raise because she wanted to buy a couch, and the couch was $800. And she said, I would like you to give me a raise so I can afford this couch. And her boss said, why would I give you a raise? And she said, because I deserve one, whatever. And he said, you know what you should really do is you should put away a penny today and then double it so that you have 2 pennies tomorrow. And then the next day, double that so you have 4 pennies put away. And I guarantee you by the end of the month, you will have enough to buy that couch and then some. And she could not believe that. But actually, the mathematics is very true there. So again, at time 0, let me just write it this way. Time 0, she will just have 1 penny. But then the very next day, she's going to double that up. She'll just put an extra penny down so she has 2 pennies. And then the next day, she'll double that up and put 2 extra pennies down so she has 4 pennies. And the next day, she'll double that up. So she'll put 4 extra pennies aside so she'll have 8 pennies. And so on and so forth down the line. ... And the question is, how many pennies does she have after 30 days? So this requires us to notice patterns. And in mathematics, patterns abound. They're everywhere. So I think that everybody here would probably agree with me that 2 is the same thing as 2 to the first, and 4 is the same thing as 2 squared. And while we're at it, we might as well say that 8 is the same thing as 2 cubed. And we might as well just say that 1 is 2 to the 0th. And you could see the pattern is set. Whatever day we're at is how many pennies she has. 2 to that power of pennies. And if you write out that function, the population of pennies that she has, she started with 1. That was her initial amount. And she would double that every day. That's the base of 2. Notice this base is greater than 1. And notice if we say, well, what's p of 0? That's 1 times 2 to the 0th, or 1. That works out. Check. And p to the first, that's 2 to the first, which is equal to 2. That works. And so on and so forth. So this is actually the model. And notice our population is increasing. So this is a good justification that if the base of our model, which in this case is 2, if it's greater than 1, then our population is increasing. It's doubling, in fact. Let's go ahead and answer Lucille Ball's question. See if her boss was right. After 30 days, she should have 2 to the 30th power in terms of pennies. And going over to Desmos here, you could see that's quite a few pennies. That is roughly, 107,3 0.741824. We have, remember that decimal place is going to move over 9 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, that's 9 units. All right. So let's see what that number is. So that is, what is that? 1 billion pennies. And this is pennies, not dollars. But of course, you could move the decimal place over 2 to figure out how many dollars that is. By the way, that's not roughly, that's exactly equal to. So let's go ahead and move the decimal place over 2 spots so that we end up with 24 cents at the end. Let's see, 814 with a comma and 737 with a comma and 10. So that's $10 million. $10,737,418.24. So that is the power of doubling, only 30 days later. So obviously she would be able to afford that couch. You could do the same trick if you try a base that's less than 1, but still positive. So if you tried a base like 1/10, then that means every day that passes, the population becomes 1/10 of what it originally was. Let me just showcase that. If I said P of t is equal to some initial population times 1/10 to the t, then at time 1, you have 1/10 of your original population. At time 2, you have 1/10 squared of your original population, or 1/100th of your original population. You could see your population would be decaying. So anyhow, that's to justify that if the base is greater than 1 on an exponential function, your population will be increasing. If it's between 0 and 1, the base is, then your population will be decreasing. In the rare case, very rare case, where a initial population is negative, which I can't even think of a case right now that's like that, then it's swapped. In other words, our function would be decreasing if the base is greater than 1 and increasing if the base is between 0 and 1. However, let me just say this out loud. You are at a point right now, if you've been watching my video series from the get-go, you've already covered transformations of graphs. So if I tell you that instead of dealing with a population function where you started with 30 million, 30 people, 30 bugs, 30 bacteria, I don't care what it is, but if you started with 30 and it was doubling every day, and then later on I say, oops, sorry, I need you to deal with this other model and it looks like this, then you know that negative on that coefficient is just going to flip the graph about the horizontal axis, which in this case is the t-axis. So you could graph it very quickly and see this result right here. Not that big of a deal. So what else do we have to review, that is? Well, we already know what an exponential function is. We've already said that this is the exponential function. And it's just important to get some language in here. It's so that we can speak the same language when we talk about exponential functions. So if the base is greater than 1, which I'm going to highlight in yellow here, then that population function or exponential function exhibits exponential growth. Again, we just wrote down a theorem, or had a theorem, that said that the function was increasing if the base is greater than 1. And so we call that exponential growth. That should be somewhat obvious to most people. If the base is between 0 and 1, then we have exponential decay. And I'll use blue for that. So if the base is between 0 and 1, the function experiences exponential decay, or displays exponential decay. Now, I am kind of hand waving here a little bit. I'm assuming one very important detail. This is assuming that P naught is positive. And that is going to be the vast majority of situations, unless it's some silly textbook problem. But I truly mean silly textbook problem, because most textbooks problems have you do graph things like f of x is equal to a negative 3 times 2 to the x plus 4 or something like that, okay? That is not a realistic exponential model. There's not a lot of reasons why you would encounter that style of exponential function in the real world. However, there is a reason in math education to actually encounter that type of function. It's because we want to make sure that you know how to graph using transformations. So there you go. We will likely do that in a future lecture, not this one. And by the way, the value of b, depending on if the function is increasing or decreasing, is called the growth or decay factor. So you either have a growth factor or a decay factor. And so if I say, what's the growth factor? Well, I'm implying, first of all, that you have exponential growth. And that also means I just want to know, what is b? And that's all the growth or decay factor is what b is. And finally, in this video, and yes, I mean finally, because I'm trying to keep my videos somewhat short so that you can take little bite-sized chunks out of them. We're going to talk about the domain, the range, and all these little special pieces of an exponential function. So the domain of an exponential function is all real numbers. You can plug any value you want in for t. So this is a critical piece of information. The domain, you can plug anything you want in for time. And that seems kind of unrealistic, honestly, because you may say, well, but if it's an exponential model, isn't time 0 like the initial population? You don't have a population before then? And I would say, yes, you're absolutely right. In a realistic sense, that is true. However, in a mathematical sense, you still mathematically could plug in negative values for time. So that's okay. The range of an exponential function, generally speaking, is 0 to infinity. And you probably, or not probably, you definitely should already know what all exponential functions basically look like if the base is greater than 1. They all kind of look like that. That's if the base is greater than 1. If b is greater than 1. And the outputs range from 0, not including 0, all the way to infinity. So when I say it's not including 0, it just means that the y values get infinitesimally close to the horizontal axis here. They will never touch the horizontal axis, but they'll get really close to the horizontal axis. And that lets me know that the horizontal axis is also a horizontal asymptote. If I draw this line in, and if I could do it on this black curve, that'd be awesome. So that is a horizontal asymptote for our function. And this is what I say in the second sentence, is that in either case, the horizontal asymptote for an exponential function is y equals 0. Oh, and the vertical intercept is 0 comma p naught. And that's just out of logic. If you were to plug in to that function 0 for time, you would get p sub 0 b to the 0th, but bases to the 0th power for exponential functions, b to the 0th power is going to be 1. By the way, you might have thought, right as I said that, wait, isn't b to the 0th power always equal to 1? Why did he say b to the 0th power for exponential functions is equal to 1? It's because any number raised to the 0th power is 1, with the exception of one number, 0. 0 to the 0th is indeterminate. We do not know what that is. And so we say we cannot determine that, or it's indeterminate. Luckily, with exponential functions, your base will always be positive, so you don't have to worry about that condition. All right. And I'll mark that on the graph here. So this point right here is 0 comma p sub 0, or p naught is what I'm calling that. There's a piece of this theorem that I didn't read, and that is, let me highlight it in blue here. So the range is 0 to infinity if p naught is greater than 0. It's actually negative infinity to 0 if p naught is negative. That's a very rare case. I want to continually tell you that having a negative population is incredibly, or a negative initial population is incredibly rare. And that's why I don't really focus on that. I don't think it's worthwhile for you to spend your time on something that is theoretically there, but realistically never going to happen. So I don't really focus on that blue highlighting too much. All right, so this rounds out kind of our introduction or our review of exponential functions, and we'll go into a deep dive in the future videos on this, but this is good enough for now.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.